Voy a presentar a Juan Cruz en primera instancia.
Muy bien. No sé si estamos viendo la cámara de Juan Cruz. No sé si ustedes la están. Estamos viendo solo la presentación. Estaría faltando la cámara. Just, I'm going to record the presentation with Zoom. You are okay with that? All are you okay with that? It's okay? Nobody have any problem? Okay.
Va a comenzar a grabar.
We'll begin once she... no vemos la cámara de la sala, Adriana, todavía.
Diego, se ve, pero se ven los de al lado.
Ah, espera, no lo veo.
O sea, si te pones como que de ver la presentación y las camaritas, cuando
Gracias.
ellos hablan, de nada.
Faltaba Carlos. Vamos a verificar que están todos porque Carlos me había quedado fuera.
Cuando estés, Diego, avísanos.
Listo. Ya nosotros nos silenciamos y empezamos.
Bueno. Vamos entonces. Buenos días, good morning. Es un honor como directora del doctorado y en nombre del comité académico del mismo presentar la primera defensa de tesis de la carrera desarrollada en la Facultad de Ingeniería por el ingeniero Juan Cruz Barria, en cotutela con la École des Ponts Paris Tech. El idioma de nuestro doctorado es en español, pero en función del acuerdo firmado se acepta que la defensa se realice en inglés. Este acto de presentación de la tesis titulada Efecto de un biopolímero sobre el comportamiento mecánico y microestructural de cementos para pozos de inyección en el almacenamiento geológico de dióxido de carbono, para obtener el título de doctor en Ciencias de la Ingeniería, tiene un triple valor. Primero, para Juan Cruz, que optó por un tema que no solo aporta al avance de la ciencia, sino que también es pertinente al desarrollo económico de la región. Segundo, porque todo el proceso de investigación permite demostrar la importancia de la cooperación entre instituciones de educación superior de diversas partes del mundo para mejorar el conocimiento. Y tercero, porque muestra que desde una universidad tan alejada de los grandes centros internacionales como la Facultad de Ingeniería de la Universidad Nacional de la Patagonia San Juan Bosco, es posible proponer y realizar programas de alto nivel científico y profesional de forma exitosa. Su director en Argentina, el doctor Diego Manzanal, de la Facultad de Ingeniería, y la doctora Analía Vázquez, de la Universidad de Buenos Aires. Sus directores en Francia, Jean-Michel Pereira y Sebastien Gabelou. I would like to thank the member of the jury for being part of this thesis defense. I give the floor to the president of the jury, Professor Santamarina.
Good morning, colleagues, and all of you in the audience. It's my pleasure to chair this meeting today. And without any further delays, I would like to introduce Juan Cruz Barria, who, as indicated earlier, is completing his PhD as a joint effort between la Universidad Nacional de la Patagonia and École des Ponts. Juan Cruz, si está listo, you're ready, we are ready.
Great. Thank you, Carlos. Can you hear me well?
Absolutely.
Okay. So, thank you, members of the jury, for agreeing to be part of the evaluating committee. This is a joint work between the Universidad Nacional de la Patagonia San Juan Bosco and the École de Pompagitech. It is an honor to me to present to you my thesis called Effect of a Biopolymer on the Mechanical and Microstructural Behavior of Oil Well Cement for CO2 Geological Storage. Can you? Carbon capture and storage is a technology that allows us to store massive amounts of CO2 in deep reservoirs. This allows us to reduce the emissions of CO2 to the atmosphere and by storing this gas in suitable geological reservoirs. However, one of the main concerns is the long-term behavior regarding the integrity of the well. In particular, this well must seal the CO2 for hundreds or even thousands of years. Also, the cement sheath must withstand the long-term carbonation effect, and the high temperatures and pressure of the reservoir allows the CO2 to be in a supercritical state, which in turn can lead to cement degradation over time. Along the wellbore, there are temperatures. Sorry. I'm sharing now. Are you seeing the presentation, members of the jury?
Yes.
Okay.
Yes, we see.
Okay.
Your slide right now is number 3.
Okay. Along the wellbore, there are temperatures and pressure gradients, and in CO2 storage, we can usually find this CO2 in supercritical states. These conditions are temperatures higher than 31 degrees Celsius and pressures higher than 7.3 megapascals. When we heat when we heat the liquid of CO2, we can see in the video the transformation towards supercritical fluid. This fluid has the density of a liquid, the viscosity of a gas, and a high CO2 content per unit of volume. This fluid in contact with the cement sheath starts the carbonation process. This carbonation process starts to dissolve the main components of cement, portlandite, and starts to precipitate in pores. If the condition permits, the calcium carbonate will be redissolved in the fluid. CO2 migrations to other rock formations. Authors have been studying this problem, and they have carbonated cement samples in laboratory conditions, and they found that carbonation damaged the specimens. And in some cases, the carbonation induced cracks on the cement, losing its integrity. One of the main problems of carbonations are the low pHD of the fluid, which can lead to casing corrosion, the loss of mechanical performance due to CSH decalcification, and the calcite dissolution may lead to cement disintegration over time. Additives are added to cement in order to improve some of their properties. In our work, we will study the behavior of nanocellulose with the mixture of cement. The nanocellulose is the smallest fiber in the cellulose fibers. It has diameters of nanometric diameter and length of 1 micrometer. Some type of nanocellulose are the free-related nanocellulose, nanocrystalline, but in this work we will focus on the bacterial nanocellulose. In this case, the Gluconacetobacter silinus bacteria is one of the primary microbial producers of this material. On the microscale, this material looks like a gel, but in the microscale, there are actually cross-linked nanofibers. Some advantages of using this biopolymer is that its production is environmentally friendly, and its production has been improved over the recent years. It also had good tensile properties when we compare it with other polymers, and is thermally stable up to 300 degrees Celsius. The use of micro and nanocellulose is a subject of interest in the research, and some authors have been studying some of these nanocellulose, like microcrystalline particles, cellulose nanofibers, and nanofibrillated cellulose. So, regarding the problem of storing CO2 and the characteristic of bacterial nanocellulose that can improve cement properties, can we use bacterial nanocellulose to improve these properties in the context of CO2 geological storage? And in detail, how bacterial nanocellulose changes the microstructure and mechanical properties of cement, and how is the durability of this cement in contact with CO2 under different environmental conditions. So the objectives of this work, of this thesis, are to determine the effect of bacterial nanocellulose on cement and to study the mechanical and microstructural changes produced by supercritical carbonation under different environmental conditions. For this, our work focused on the carbonation of cement by performing an experimental program analyzing the effect of bacterial nanocellulose on cement under two different curing conditions. The second part regarded the numerical simulations where we use a coupled mechanical model in order to determine the dissolution and precipitation processes of the cement components and how was the poromechanical behaviors being modified over time. Now we'll see the materials and methods used on this thesis. We use bacterial nanocellulose from the Institute of Technology on Polymers and Nanotechnology, and we blended with mixture with fresh water in order to, and we perform ultrasound in order to have a better distribution of bacterial nanocellulose in the mixture, in the final additive. We use API class G cement of higher sulfate resistant, along with fresh water and superplasticizer. We use 5 types of mixtures, the first one with no bacterial nanocellulose in it, and the others up to 0.20% of bacterial nanocellulose by weight of cement. And we also use 2 types of specimens, cubes and cylinders, with a water to cement ratio of 0.44. Now, in order to determine the effect of bacterial nanocellulose on cement, we had to characterize this material. So we performed free fluid test and consistometry test on the fresh state to determine the free fluid content and thickening time. We performed dynamic mechanical analysis, uniaxial compressive strength, triaxial test, and ultrasonic wave measurements on set cement to determine the strength and stiffness of the material. We performed thermogravimetry analysis, mercury intrusion porosimetry, scanning electron microscopy, and X-ray diffraction on the microstructure to determine the hydration microscopy and the crystalline phases. All of this was done on 2 different curing conditions: low temperature at 20 degrees for 28 days, and high temperature of 90 degrees over 10 days. After this, we carbonated our samples at high pressure and high temperature for a period of time. And we performed more or less the same test as before, considering both curing conditions of low and high temperature. Now I'll present to you the effect of bacterial nanocellulose on cement. When we first added bacterial nanocellulose to cement, we saw that viscosity increased. This means that the bacterial nanocellulose was retaining part of the mixing water. In this case, we determined the initial consistency and thickening time of the reference sample, and we tried to emulate this with samples with bacterial nanocellulose. In this case, we needed 0.35% of superplasticizer in order to have a similar viscosity of the reference sample. when we let this mixture to be in under static condition for 2 hours, we can remove the free fluid from the top, which is separated from the mixture, and compare it with the total weight of the mixture. In this case, the free fluid depends on the superplasticizer content, and we see that it decreases with the content of superplasticizer. However, when we add bacterial nanocellulose to the mixture, we see that it follows the same trend, but with lower amounts of free fluid content, meaning that less sedimentation occurred, and that bacterial nanocellulose is helping in preventing the fluid breakouts. Now that we have seen that bacterial nanocellulose modifies the fresh state, we will see how it modifies the hardened cement. We will study the microstructure of cement. Initially, the reference cement had capillary porosity of 20% with a characteristic peak of 50 nanometers or 0.05 micrometers. But when we added bacterial nanocellulose, we saw that this value decreased below values of 15%, but the characteristic peak in this case was not shifted. To determine the Portlandite content and degree of hydration, we heated the sample. So we can determine the content of Portlandite, for example, by transforming the lost weight at 420 degrees to the real content of Portlandite of the solid phase. We can do the same thing by taking initial and the final temperature in order to determine the degree of hydration. In this case, we saw that bacterial nanocellulose, while we are increasing the bacterial nanocellulose content, the content of Portlandite and degree of hydration increases as well. We also saw this on X-ray diffraction test when we saw that the content of Portlandite was increased while the anhydrous cement was decreased. And we also saw some small quantities of calcite. These results indicate that bacterial nanocellulose enhanced hydration over time. This is probably the reason why the cement strength of bacterial nanocellulose was stronger after 28 days of curing. Now that we have seen that bacterial nanocellulose modifies the fresh state and hardened state of cement, let's see if it modifies the durability of cement against carbonation. The carbonation test consists of a CO2 cylinder, a CO2 pump, a titanium cell, and a heat controller. We chose the temperature of 90 degrees Celsius, 20 megapascals under static conditions for 30 and 120 days. We used cylindrical samples using both curing methods of low and high temperature. After carbonation of the sample cured at 20 degrees Celsius, we saw that there was a major degradation at the top of the samples, but they were not completely carbonated as we expected. We also saw that density increased after 30 and 120 days of carbonation due to the precipitation of calcium carbonates in pores. To generate interfaces in cement. For example, in this case, if the chemical reaction goes in this way, the zone near the exposed edge will have a calcium redissolution zone right next to the carbonation front and next to the Portlandite zone, dissolution zone, and the unaltered core cement. The carbonation front is characterized by having a great high crystallinity, where calcite crystals start to precipitate here, as well as aragonite and baterite crystals, which are polymers of the calcium carbonates. Knowing that we had at an heterogeneous material, we needed to study the exposed edge, the area near the exposed edge, and the interior of the cement. And we saw that at the exterior area, that porosity decreased over time from the initial 20% of the reference cement to around values of 5%, while the interior more or less had the same porosity, but the characteristic peak was shifted towards smaller pores. As we expected, carbonation reduced the capillary porosity of the cement sample. We determined the total porosity of non-carbonated samples, and it was around 40%. But after 120 days, we saw that the most degraded part had values of 30%, and the interior had values of 45%. Now that we have determined the total porosity and capillary porosity, we can calculate the gel porosity, which are pores with a diameter less than 10 nanometers. And we can see in this graphic of a point near the exposed surface that total porosity decreased over time, as well as capillary porosity. And initially, gel porosity decreases as well, but after 120 days, it starts to increase again. This happens for all the three types of mixtures that we use for carbonation. This shows that carbonation modifies the microstructure, reducing larger pores and increasing the smallest one. In the same manner, we determine the portlandite and calcite content of the sample at the exterior and in the interior. And we saw that at the exterior there was no portlandite, and there was a high carbonated material with calcite and aragonite. While in the interior, portlandite was slightly reduced compared to the non-carbonated cement that we saw before. Now that, the reduction in porosity and the precipitation of a stronger material in pores may lead to believe that strength will increase over time. However, this is not the case for our samples. After 120 days of carbonation, we saw that compressive strength was reduced by 30% on the reference samples, and for the bacterial nanocellulose samples, it reduced 16% and 23%. We saw a similar trend on the Young modulus, where the reference sample lost 36%, and the other mixture lost 9% and 20% respectively. Here we can see the development of strength over time after 30 and 120 days of carbonation for the reference sample and the sample with 0.15% of bacterial nanocellulose. We can conclude that in this case, carbonation reduces cement strength, but the specimens with bacterial nanocellulose are less affected. We also perform isotropic test in order to determine the stiffness of the material. The isotropic test consists in applying an isotropic loading and to measure the volumetric strength. In this case, we took a saturated sample and we put it in a triaxial cell where we placed 4 radial LVDTs and 2 axial LVDTs in order to determine the displacement of the sample. The objectives of this test is to determine the bulk modulus under drain and undrain condition of the specimen. To calculate it, the bulk modulus is the slope in a confinement pressure against volumetric strain graphic. we saw that before carbonation, the values of the bulk modulus were more than 11 gigapascals in this case, and it depends on the confinement pressure. But after carbonation, we saw that all samples had bulk modulus lower than 10 gigapascals, meaning that carbonation reduces stiffness of the material over time. To explain this, we examined the exterior part of the material of the cement, and we saw that there is a large area of high porosity. This area shows very low content of portlandite, of anhydrous cement, but a large amount of aragonite, which is an unstable polymorph of calcite. Here the black numbers are carbonated values, and on the brackets we have the values before carbonation. From here, we can see that the exposed edge is more porous due to the calcite dissolution, and this reduced the stiffness of the material that we saw on the triaxial tests. Now that we have characterized this carbonated material, we will see if there is an effect of bacterial nanocellulose when we cure this material at high temperature. In the same manner, we did the same characterization as before, and in this case, on the microstructure, we saw that capillary porosity but total porosity was maintained around 40% because the water to cement ratio was maintained of 0.44. In this case, the bacterial nanocellulose did not show any improvement in capillary porosity. It did not reduce capillary porosity, and neither on the X-ray diffraction test we didn't see any change in the crystalline phases, having the similar components as the reference samples. This means that this curing method inhibits the bacterial nanocellulose effects. When we carbonated these samples, we saw that the carbonation was 10 times higher than the previous curing method. We also took the capillary porosity in the interior and the exterior as before, and we saw in this case that the porosity was reduced to 14%, and it wasn't seen any contribution of bacterial nanocellulose. In contrast with the previous curing method, we saw in this case strength increases inside the cell, probably due to the hydration process that is still taking place in the carbonation cell at the same time as the carbonation. So in this case, bacterial nanocellulose does not improve cement durability against carbonation. That we did. In the characterization of cement in samples cured at low temperature, we saw that the addition of bacterial nanocellulose increases viscosity, it reduces the free fluid content, that reduces the capillary porosity, and enhance hydration, and increases cement strength. When we carbonated this cement, we saw that for all samples, that carbonation increased density, that total and capillary porosity decrease over time at the exposed edge, that total porosity increases at the core while portlandite content decreases, the strength and stiffness decrease over time, and the exposed edge is more porous. When we added bacterial nanocellulose, the lower capillary porosity limits the entry of CO2 into the core of the sample. And it also shows higher values in their mechanical properties in absolute and relative terms after carbonation. When we modify the curing conditions and we cure it at 90 degrees, for all samples we saw that capillary porosity is higher, so the carbonation process is faster. That total porosity decreases over time and that the strength and stiffness increases as well. In this case, the bacterial nanocellulose does not improve any mechanical or microstructural properties of cement. As we saw that we had an heterogeneous material, a modeling tool was needed to simulate the carbonation front. The dissolution and precipitation process is required to estimate the material response to stresses. This is why we model the carbonation process. I will give you a brief summary of how this model works. Carbonation induces chemical variations and porosity as well. This modifies the mechanical behavior of the specimen, and porosity changes also modifies the diffusion and advection phenomena. By modifying the diffusion and advection, also the chemical reactions are limited over time. This is the Chemo mechanical couple model that we use and that was implemented in a finite element method in the code build. This code considers the conservation of the fluid mass, the conservation of the molar quantity of CO2, and the conservation of momentum. The first one considers the fluid compression, the formation of the porous media, chemical reaction, including water release, and Darcy's law. The second one considers the chemical reactions and the diffusion and advection phenomena. However, the current model does not consider the dissolution of calcite, as we have seen on the experimental tests. So a model of the calcite dissolution was implemented in the code by establishing a condition to determine if calcite was dissolved in a particular point. And this model is a function of the CO2 concentration in the fluid. For this, we use Shen's model which simplifies the chemical equilibrium of calcite in one single variable called sigma. This variable sigma depends on the mole of calcite and portlandite, on the constant of equilibrium of calcite, and its ion activity. Under our curing conditions of 90 degrees, we can determine the R constant of the carbonation process, and there are equations that links this that relates this constant, and we can determine the concentration of carbonates in function of the concentration of CO2 in the fluid. With the concentration of carbonates, we can determine the ion's activity in a determined point of cement, and thus calculating the value of sigma. If this value of sigma is less than 0, this means that there is no calcite present in that considered point. The mechanical behavior was developed with a poroelastic constitutive model, which relates stresses with strains and the material stiffness, as well as the porosity and pore pressure. The values of K, G, B, and N are affected due to carbonation over time. For this, the model uses a homogenization tool to consider the contribution of each cement component. The overall stiffness of the material will be the sum of each cement of each component property. And when we carbonate this material, we will see that the chemical composition and porosity modifies, and as well the considered media will be modified over time. In addition to the carbonation damage, the program also considers an isotropic damage, which simplifies the equation to a single variable d, and it uses a Drucker-Prager damage criteria for high confinement. The calculation of the damage depends on the Drucker-Prager criterion, the stiffness, and the imposed deformation. And from here we can determine the new stress state as well as the new damage moduli. No sé dónde se quedaron.
Juan Cruz, can you begin with the slide 44? From the beginning of the slide 44, please.
No me estaría cambiando la diapositiva. Ahí está. Here. Okay. So, to simulate our samples, we took 1/4 of the cylindrical samples that we use in our test, and we took the fluid properties at 90 degrees of viscosity, compressibility, and density, and the cement properties taken from the uniaxial compressive strength test. To determine the phases of cement, we considered porosity was taken from the MIT test results. The Portlandite content was taken from the TGA analysis. And initially, we didn't consider any carbonates in the samples, and the content of bacterial nanocellulose used was the content that we added in the experimental test. The value of CSH and inner components were taken from literature, and the inner components are aluminates and anhydrous cement. To prove the damage model, we loaded and unloaded the sample of a specimen cured at 20 degrees Celsius until failure, and we see how damage increases over time into a value of 0.45, which was the limit criterion of failure. And we see also that bulk modulus linearly depends on the damage, and it also degrades over time. The good thing of this model is that it can simulate any other mechanical loading, including triaxial tests. The specimens that we carbonated in the cement in the carbonation cell. In this case, we use the values that we use in the experimental test with pressure of 20 megapascals, a CO2 concentration of 1200 moles per liter. With the CO2 concentration, the model can also determine the Portlandite content, the CSH content, and the carbonate content of the material. If we different sections, which are the same sections areas that we saw on the experimental results, with the calcium dissolution zone, the carbonation front, the Portlandite dissolution zone, and the unaltered core. The model the good thing of this model is that it can also reproduce different carbonation scenario with different loading types. We did a uniaxial compressive strength test of the non-carbonated cement and carbonated cement fitting the final strength of cement, and the model calculated the elastic modulus of this material. And we saw that and we saw that these simulations are in agreement with the values obtained from the experimental results. We also did the same thing, but with samples, with specimens cured at 90 degrees. In this case, we modified the cement properties of compressive strain and the volumetric fraction of each phases, correspondingly with the values that we obtained from the experimental results. For instance, in this case, by fitting the initial and final porosity, we can determine the diffusion of CO2 in this cement over time and determine the porosity on each point, and also we can calculate it further. We can estimate the diffusion of this cement over time if we want so. So a brief summary of the simulation experiment is that the experimental results were used to calibrate the carbonation model. A carbonation dissolution model was adapted to the existing code. The simulations represent the progress of carbonation and the poromechanical changes produced. And the simulations are in good agreement with the experimental results obtained. So if we back to our original question of how bacterial nanocellulose changes the microstructural and mechanical properties of cement, we can say that for samples cured at 20 degrees Celsius, that bacterial nanocellulose increases the consistency of cement paste and reduces the free fluid content. It increases the degree of hydration and decreases capillary porosity as well. And it improves the overall mechanical behavior. For example, the uniaxial compressive strain is 15% higher than the reference cement. And the second question, how is the durability of bacterial nanocellulose cement in contact with CO2 under different environmental conditions? We saw that carbonation reduces the mechanical behavior and stiffness of all samples of a specimen cured at 20 degrees Celsius, and that these specimens were not fully carbonated. The specimens with bacterial nanocellulose show higher values of their mechanical properties compared to the reference cement in absolute and relative terms after the carbonation process. But when we cure our samples at 90 degrees, the stiffness, strength, and microstructure do not show significant changes when we add bacterial nanocellulose. The new features of the model can reproduce different carbonation situations. This model fairly reproduces the dissolution precipitation process of cement components and the variation in their mechanical properties of cement. Some perspectives of this work: more detailed work on the effect of bacterial nanocellulose at different curing temperatures will be relevant to perform, also considering different water-to-cement ratios. It will also be of interest to make a comparison between cement cured at different ages and carbonate them under the same conditions. Tests studying the permeability of cement during the carbonation process will be also of value. And a crystallization pressure model could be added to the code to assess the damage caused to the sample during carbonation. I hope that you have enjoyed this presentation, and I will be looking forward to your question. Thank you.
Thank you, Juan Cruz. And I think that we are ready to continue unless you tell me that you need a couple of minutes.
Sorry?
Are you okay to continue? Are you ready to continue?
Yes, yes.
You need a couple of minutes.
No, I'm ready.
To take a break. Yes? Okay. Excellent. So Juan Cruz, the committee, and to all of them, all the individuals in the audience, the committee consists of the following individuals. There are three reviewers: Antonin Fabri from the National School of State Public Works in Lyon, Celina Bernal from la Universidad Nacional de Mar del Plata y CONICET, Argentina, Martín Sánchez from YTech, Argentina, There are two examiners, Teresa Piquet from the Universidad de Buenos Aires and myself from King Abdallah University of Science and Technology. And of course, there are three individuals you know very well who have been intimately involved with your thesis. Professor Jean-Michel Pereira from École de Pont, Siavash Gapeslu from École de Pont, and Diego Manzanal from EPN Madrid. So we're going to proceed in the order that I have just indicated. So let's begin with Professor Antonio Fabri from Lyon.
Okay, thank you, Mr. President. Can you hear me? It's okay? Everybody?
Yes, we can hear you.
The importance is Juan Carlos is important.
Oh, okay, perfect. So first of all, before beginning my question, I want to congratulate you for this very extensive work, which is quite amazing because there is very huge experimental works on basically two main subjects. Actually, there is sort of two kind of theses because we have a thesis on BNC addition on cementous material and as well on carbon supercritical carbonation, which is not easy testing methods because it's high pressure, high temperature methods, and so it is quite complex. And as well some modeling activities, chemio-mechanical simulation. So it is quite impressive work of that, and I want to congratulate you first for that. And at the second point, I want to congratulate you as well for your presentation, which was very clear, and which helped to understand some of the points of a manuscript, because manuscript is sometimes quite dense. So it was very good to have a better view of how the experiments can be linked together. But I will go further on my points during my question. But it was very interesting presentation for that. Yeah, but for sure, my duty today is to ask you some questions, to have some information and to some additional information of your work. And so I will begin following my report with bibliographic data. Actually, so the main goal was to study BNC for well-work cements. So for underground conditions. And there is a very interesting bibliographic analysis on cement hydration and cement carbonation, but it lacks, as for me, some information on the impact of pressure and temperature on these two chemical reactions. So it is the first part of my question. What is your opinion about that? So how temperature and the pressure can modify these two chemical reactions? And the other one, so it's a question in part, and the other one will be, so how have you shown why 90 degrees and I don't remember exactly. I think it's
20 and 90 degrees.
20 megapascal. Yeah. Yeah. Why these temperature and pressure conditions? What have you chosen these temperature and pressure conditions, and not other? Are there some kind of future temperature, or why?
Yes. We wanted first to have a completely carbonated samples. From literature, we saw that using a carbonation at 90 degrees Celsius and 20 megapascals, the author were arriving at this point. and it was also the inside the conditions that of the triaxial of the carbonation cells that we had, and we wanted to exploit to the maximum the ability of this carbonation cell, which was the maximum of 20 megapascals, and a temperature of 90 degrees Celsius. But most of it was related to the literature that they were using this temperature and pressure.
Yeah, because why I asked you this question? Because yeah, we have seen that with BNC, so at this kind of pressure and temperature, the results are not as good as expected. But I wonder if with this kind of study of hydration process, in particular hydration process with BNC, with pressure and temperature, we can have a better range of a domain in which BNC can be really suitable, can be good, even in supercritical conditions, because you can go to supercritical condition far below these conditions. So these conditions are very extreme conditions, but there is some supercritical condition for lower temperature and lower pressure. Do you agree with that?
Can you repeat the question, please?
Yes. So my question is typically, okay, you take very hard conditions with very hard pressure and temperature conditions, and yeah, you can have supercritical CO2 states for lower temperature and lower pressures, and in the context of geological storage of CO2, we can have really lower conditions as well. So my question is that maybe for lower values of temperature and pressure, maybe the effect of the NC will be more important than the condition we have chosen in the physics.
Yes, that was one of the perspectives that I think that I wrote. Yes, probably by curing the cement samples at lower temperature and carbonate them at lower temperature will probably improve the working mechanism of the bacterial nanocellulose. Yeah.
Yes. So my point of view. So before trying several temperature and several pressure, maybe a kind of bibliographic analysis on the effect of temperature and pressure on both BNC and hydration, because I think there is some literature that can help you to choose this kind of threshold temperature and pressure.
Yeah, that will be an interesting work to determine the properties of this of curing the cement at different temperatures, and as well carbonate them at different temperatures as well, in order to determine how it's really affecting and to which point the bacterial.
I do not answer, and I do not
Can you repeat the answer, please?
Yeah, that it would be a very good study, I think, to see how these properties, the cement properties, are modified with temperature, and how is the mechanism of bacterial nanocellulose is working on them, until which point we can use, until which temperature we can use the bacterial nanocellulose. Because in this case we had only the initial value of 20 degrees, for example, and we cured it also at 90 degrees, which is quite extreme. But yeah, it will be really good very interesting to know what happens in the middle temperatures. Yeah.
Oh, okay, so I will go now to the experimental analysis. And yes, so my first question is concerning, so it's just an explanation because I don't really understand that reading the manuscript, and I did not manage to understand that as well during your presentation. So you've got two chlorine methods, and for the second chlorine method, you consider the first one, which is at ambient temperature, which is quite common chlorine methods, and the second one was a chlorine method, which at high temperature. But I don't understand two things. So the first thing is what is the state of the sample when in the chlorine method B, when the sample is put in the carbonation reactor? Is it saturated or is it dry?
Mm.
So, have you resaturated the sample before putting it for carbonation, or is it putting dry into the carbonation reactor?
All cement samples were fully saturated before putting them in the carbonation cell. So yeah, they were put in water before the carbonation test. Can you hear me now?
Start again your answer. Yes. Sorry for it to be annoying. It's just that your sound is coming on and off. So could you please repeat your answer?
Yeah.
For the protocol of full saturation.
Yes. It was like you said. We saturated the samples under vacuum. Yes. Before putting them in the carbonation cell.
Okay, so yeah, why do not have why you don't have tested a situation where you got the sample at high temperature but with no drying? Because maybe this drying wetting process can damage the sample, no?
Dry wetting. The dry wetting. We wanted to first to.
Because you make a cure. Yeah, I let you answer. Sorry.
We wanted to both carbonation methods to be comparable, so that's why we decided to saturate them both before carbonation. But that was the main reason.
Yeah, but in that way you got one situation where the sample were never dried, okay, by one understood, and the second one when you make hardening at higher temperature, and then you dry the sample, or you dry the sample after today the number, you resaturated it. Was it possible to test? Why do not have? Why don't you have tested the case where the sample is the rehydration is made at higher temperature but with no drying?
Yes, that was main because we considered some experiments from literature, and the other reason is that we wanted to have a really porous material in order to have a fully carbonation material after the process, but mainly from literature. Yeah.
It's very really this. But sometimes maybe you can put your slide element to illustrate the great number of experimental tests you have made. And sometimes, okay, some of the tests gives the same kind of results. Why have you, for example, okay, for strength and stiffness, you have four tests. Some of them are, there can be some kind of overlap between some of these tests. So why you decide that? And another question is particularly on triaxial test, because you make triaxial test and you make triaxial test of saturated sample with measurement of pore pressures, but you do not use this pore pressure information in order to have, for example, the more Coulomb or Patagonia parameters. So why?
So regarding the first questions, we did this test because there was the test that we had in our laboratory, dynamic DMA, the uniaxial compressive strength, which is very characteristic of cement. We had the triaxial cell, which is gives a lot of information, and the ultrasonic wave measurement also is a very easy tool for using it. So that's why we chose this test. And the second one, which can you repeat me the second one, please?
Yeah, you made some triaxial tests, and after that, during the modeling, you use private criterion. So, and since you made some consolidated grain triaxial test on saturated sample with test to have access to some of the kind of equation, friction factors.
Yeah.
What is test used for that purpose?
Yes, actually we tried to do that, but we didn't have enough information on this test, on the triaxial test. Actually, it was quite a challenge to prepare the triaxial test, and a lot of samples were broken before testing them. While they were testing, it was quite difficult to obtain the triaxial value of the deviatoric stress in order to determine the phi parameter on C. But that was initially the idea, and given the fact that we had also 3 types of different mixtures, the amount of tests necessary in order to determine this parameter was quite a challenge. It would have taken a lot of time. Even I think one thesis we can only do triaxial test to determine this parameter is quite a very challenging. It's a difficult process to do the triaxial tests. It takes a lot of time, so we just didn't calculate it, just for that reason.
Way to reach this value. So have you tried to do that to reach the value to the driving value?
I hear you. I don't hear you so well, Antona. Can you repeat the question?
Yeah. In the theory of pore-elasticity, bulk undrained and drained bulk moduli are linked together. So to invent through the Biot modulus and Biot coefficient. And the Biot modulus itself is, can be estimated through the Biot coefficient and the porosity and the bulk modulus of the skeleton. So maybe it would have been interesting to compare these two moduli, so the drain and undrained. So have you tried to do that?
Yes, we try it, but just here in the presentation we just put all the tests. But yeah, I think we need a more detailed work on comparing each test of drain and undrained conditions, even for each type of mixture used.
Okay. So because you are at this, I have not planned to ask you this question, but since you have this slide just in front of me, so how do you calculate your effective confidence? Is it the Tesis effective?
Yes, yeah. Yeah, it's
this effective strength I use in your model after that?
This is the effective stress, the effective confinement, the effective stresses that we use afterwards. Yeah.
Okay. Yeah, maybe I will ask you some question. I have time. Maybe I have 5 minutes left, so I will ask you some question on the simulation part. So yeah, I have a question in the simulation part. Is that I do not yet understood if you consider that if you consider equilibrium or kinetics for your chemical reactions, because it is written the both in the manuscript, unless I have misunderstood some things. You say that, well, yes, we consider equilibrium, but after that you put a kinetic law. So do you consider kinetic or equilibrium for your chemical reactions?
We consider the chemical reactions as the previous presentation, and that the reactions are instantaneously. That calcium carbonate precipitates instantaneously.
Okay, so because you put a kinetic law in your manuscript, so it was not you. So you assume that all the reactions are instantaneous.
Yeah, I think I have to correct that.
Because I think that in Bill you can consider some kind of reaction kinetics, and maybe use some kinetics can be interesting if you want to see the dissolution front and the carbonation front, to have a better separation between both, and maybe to scan this porosity variation in the uncarbonated zone, which is one important thing that you have noted, underlined in your experiments, so that this porosity variation. And maybe I think that if you want to model that, you need to use some kind of kinetic law, and maybe the equilibrium will not be good to see that. It's only my impression, but maybe I'm wrong. So we'll ask you a last point open question. So, okay, with your simulation tool, which is really powerful and interesting, maybe two questions. Yeah, but I'll begin with this one. So with this numerical tool, so you manage more assumptions of your model, or more 2 years more. What kind of simulation do you think that it would be interesting to do with your code in order to scan some particular phenomenon? I don't know if you are well understood my question.
Well, actually, this is not my code. I just modified it a little bit. It's the code of Valin, and yes, what I wanted to do in this presentation was to use this tool in order to see how was the carbonation front advancing in our experimental results. But this tool can be easily extrapolated to a wellbore in a wellbore, considering this in the CO2 storage. And I think it's easier because you can, in that case, you can only use, instead of using a 2D model as I use it here, we can use 1D model, and it will be easier to calculate with using the code, right? I mean, it will take less time that this one that we took off using 2D.
It was not exactly my question. It was better in order what kind of simulation can you make in order to test this code, and which should be the numerical tests that will be interesting to make and to compare with experimental data in order to test the code and to modify maybe some kind of assumptions of this code. But I understand that it's not really your code, so so I will not go further on that point. And so my last, bit in time, it's okay, Mr. President? Can ask my last question?
And the last one, please.
Yeah, well, I can finish now.
Go ahead. Go ahead.
Okay, so yeah, I got a last question. So you use for the permeability variation. So you use a poor law for the permeability variation with porosity. With I think constant poor parameter. So yeah, it's okay for the first action. It's okay, but what kind, given the experimental data you had, do you have another way that can be used in order to model the evolution of the permeability with carbonation?
The evolution of carbonation, you said? Sorry?
No, the evolution of permeability. So the evolution of permeability. So to take into account the permeability with carbonation, you use the power law with a constant power parameter, constant A. So basically, when the porosity change, the permeability change.
Yeah.
Given the experimental data you had, do you think that may be much more complex, but maybe another way to simulate this variation of permeability with the carbonation?
Yeah, this model, to determine the permeability and diffusion in the model, it only considers porosity. We try to perform some permeability test, but I didn't put it on the thesis. We can, but
we are losing
can you hear me now?
Yes. Now, yes.
No. Now, I mean that I wanted to say that this code to calculate the permeability and diffusion only uses the porosity. And if we want to determine, we can say the constant of diffusion, we can perform permeability test to have a more complete, to have the parameters needed to improve this model. But we didn't have time to do a permeability test on this case.
On that note, if I may allow Dr. Fabri, probably will continue and we can always come back to you. Would that be
Yeah, okay, I finished.
Thank you, Antonio.
So thank you for your answers. And I first for your base of content so to invite Mr. Defense and so Mr. President. I stay my question right now.
Thank you.
Thank you.
Let's continue next with Dr. Bernal from Universidad Nacional de La Plata, de Mar del Plata. Selena, the floor is yours.
Okay, thank you very much. I understood that Martin Sanchez was following, but I think that was wrong. It doesn't matter. I am from the University of Buenos Aires at the concept from Argentina. I studied at the National University of Mar del Plata, but now I am at the University of Buenos Aires. Thank you very much.
I apologize.
Okay.
Thank you.
Thank you very much for the invitation to be a reviewer and also for the presentation. Of Juan Cruz was very clear, and I understand many things from his presentation. I wanted to ask some questions, not about formal style that I detailed a lot in my report, in my previous report. I only want to ask some questions more specific, more related to more important issues about, for example, Juan Cruz, you mix the components in an homogenizer, and you suppose that the agglomerates were broken. Have you measured some issues about the agglomerations to be sure that they were broken?
Sorry, can you repeat the question? What was broken? Sorry, can you repeat, please?
The agglomerates, the bacterial nanocellulose agglomerate. You said that they were broken because of the homogenization, but I don't know if you have any proof about this change in the dispersion of the bacterial nanocellulose. So the question is, are you sure that the bacterial nanocellulose agglomerates have been broken during homogenization?
For what I understand, we performed the ultrasound in order to have a better distribution of bacterial nanocellulose in the final additive. And actually, I don't understand. They were not broken. I mean, when we mixed it with the cement, we just they had this process of ultrasound, but I didn't say that they were broken.
Because the question is related to discussion about dispersion and distribution of bacterial nanocellulose within the cement. Because for usually with nano reinforcements, there are many problems regarding to dispersion and distribution of the nanofiller or nano reinforcements within the matrix in nanocomposites. So, what do you think about this in your mixtures? Because you should discuss this issue in more detail.
Yeah, the process that we use of blending and then performing an ultrasound was an advice given by my previous supervisor, and we did this because we had the tools and some knowledge of it. But yeah, I think for me, we first have to ensure that the bacterial nanocellulose is better distributed. I think they are analyzing this. There are some researchers that are analyzing how how to distribute this nanocellulose, but this was not the main focus of my thesis, and I didn't explore this in depth.
Okay, yes, I think that it wasn't your main objective, but I wanted to know if you try another RPMs, for example, or another processing conditions in order to change dispersion or distribution of the reinforcements. Another question is about where you found that the bacterial nanocellulose increase the slurry viscosity, yes? And you put that it was because of the water retention properties of the bacterial nanocellulose. But is it the only reason for the increase in viscosity of the slurry, or maybe the presence of bacterial cellulose itself the reason also? What do you think about this?
I think, for me, I didn't study this, but I thought as well. First, I think there is like a physical effect of having a large superficial area. This makes we need more water to wet this surface. But I think that there also a chemical process, a chemical effect. But I didn't study it yet.
Okay. This is I wasn't sure about your explanation in the text, so I have this out. Another thing is about dynamic mechanical analysis. You found that for the lowest content of bacterial nanocellulose, you found out the stiffness decreased, and with higher contents of bacterial nanocellulose, the stiffness increased. Can you explain this effect, or do you have an idea to explain this effect? The lower stiffness for the lowest content of bacterial nanocellulose?
Well, probably that was due to some heterogeneity of bacterial nanocellulose itself. But yeah, I think probably that was from the previous question. I think it comes from this way. Yeah.
Okay. Another question is related to will you talk about porosity? I found that you mentioned microcracks in the measurement of porosity. I don't understand clearly this relationship because I don't know, perhaps it is my lack of knowledge about this kind of measurements in your materials, but I don't know how to relate microcracks with porosity in the measurements. Can you explain
Yeah.
this?
Yeah, that actually it's not. I only have one figure here, but I'm saying micro cracks because on the in this graphic of where we can find the characteristic peak of the MIP, we saw that at first, the blue one is the 0 day, but we saw that after 30 days there was a slight increase on bigger pores here. But after 120 days, these pores disappeared again. So that's why I'm saying that probably there was small micro cracks that afterwards were filled with calcium carbonates.
The confusion comes from the term itself, because I think that porosity means the presence of pores, of course, and microcracks is another issue. So perhaps it is more in a specific language or something. I don't have so many questions because many Professor Fabri asked you many things, but I have another question about how can you explain the high strength of your cement in the presence of bacterial nanocellulose in terms of the strength of the nanofibers? How can you explain the increase in the compressive strength of the modified cement in relation to the original cement without bacterial nanocellulose?
Yes, we didn't study in detail how is the effect of bacterial nanocellulose, how is the mechanism, but well, actually, it's in this case of cement cure at 20 degrees during 28 days. This allows the cement to be very to have very low porosity and be very consistent, and this we think that allows bacterial nanocellulose to develop a network inside the cement that helps cement to it's like having nanofibers in there, so it helps in increasing strength. That was why we think that after carbonating at 90 degrees, as we have a very large porosity, capillary porosity, in this case bacterial nanocellulose was not working because the failure just went through the capillary porosity and not it was most due to the capillary. Okay, can you hear me? I go again. Okay, so okay. No, I wanted to say that cement, when we cure it at 20 degrees and 28 days, it's a cement with low porosity, and this is maybe helping CO2 the bacterial nanocellulose to have a network inside cement, well connected. But for example, as we saw curing at 90 degrees Celsius, that as we had a larger porosity of 35%, even by adding bacterial nanocellulose, this didn't modify the mechanical behavior as the cement cured at 20 degrees.
Okay, yes, type of crack bleaching or something like this. You put some schemes in the manuscript, but then you explain differently in the part of the compressive strength results, and it was confused. I was confused. I think that in the micrographs, you can add some arrows and labels in order to clarify what you are talking about. I put some specific comments in the previous reports. And I also agree with other reviewers about the reason why to use the carbonation conditions and also the curing conditions. I'm not sure. I couldn't understand why did you use these conditions for curing, for example?
Okay, so firstly we used 20 degrees Celsius to cure the samples because it was the easiest way that we were using in the lab, and it's already very standardized. But as we saw that carbonation was not affecting these specimens, it was not a large carbonation, and we wanted to have the samples fully carbonated. We did a second curing method, which is the one at 90 degrees, in order to.
I do have more questions related to concepts. I have some comments about formal things, as I mentioned before. I want to congratulate you and your advisors because the work is very complete. You performed a lot of experiments and also experimental work, but complemented by modeling. This is very important, I think. Not only modeling or not only experimental, the combination is very useful and very actual, of course. And thank you very much for your answers and also your very clear presentation. An excellent work. Thank you very much.
Thank you, Selina.
Thank you. We'll continue next with Martin Sanchez.
Hello.
Martin, go ahead.
Okay, thank you very much. Juan, thank you very much for your presentation. Congratulations, it's a great work. I think the modification of the cement to improve some properties in the cement is a subject of interest, either in the oil and gas industry and in the injection of CO2. How my colleagues said before, I think the main result of your work is the complete characterization of the cement. You did a lot of tests. You ran different tests for different properties, and this is very, very interesting. Your presentation was also very interesting. Thank you. The problem with paying one of the last is that the previous one have asked my question, but I have a couple. My first question is about the confining pressure. You say that you had a lot of problem with the triaxial test, and in one question that Dr. Fauri asked about the more Coulomb parameters, you say that you obtain different tests with errors in the parameters. I didn't find consistency in the confining pressure. You ran tests at 11 megapascal, 9 megapascal, 12 megapascal, and in the same way in 20, 21, 22, or 30. Why do you decide to run this kind of confining pressure for the triaxial test?
Yeah, firstly, we had an ambitious plan to performed confinement pressures of 5, 15, and 25, I think. But it was when we started doing this, we found some problems, particularly with the pore pressure. So the first, let's say, the first tests that we performed were chosen. For example, 5 megapascal of confinement pressure and 2 megapascal of pore pressure, and to see if it was working. But afterwards, we started to do the same at 15 megapascal, for example, and we found that the samples were being broken. So what we did was slowly increase confinement, and assuring that the pore pressure had more or less the same difference. Like I think it was 5 megapascals, and this made that this might have different effective confinement pressures in this case.
Okay, thank you. In the same way, for the triaxial test, you explain in the manuscript that you run some poroelastic test, the skeleton coefficient and the Biot coefficient. I didn't see some result about that. Did you run this test in the triaxial test? Did you obtain this kind of coefficients, and could you use that in the numerical model?
Yes, we were able to obtain, I think, 2 or 3 Biot coefficients, but we also had some problems when we performed an drain test. So we saw that it was around 0.33 for cements, and we continue using this value for the calculations.
Were the problem in the carbonation samples or in all the samples? I think that with lower porosity it's more complicated to obtain this kind of coefficient, but maybe in the samples with only the nanocellulose without carbonation is more possible.
Yeah, I mean, having a very low porosity makes it harder to saturate this sample, and in some cases when we were performing the isotropic test, the pore pressure was not going up, so we were not able to calculate the Biot coefficient in that case.
Okay, thank you. What about the HP? Selena before me asked about the chemical reactions, the HP with the cement. You did some experiment with the free fluid and you obtained high viscosity, and I understand that you use the HP to improve this kind of behavior. But the amount of HP that you use is more or less the same as the nanocellulose additive. Do you think that the HP doesn't affect the mechanical properties of the cement?
Yes, let me. All right. So we performed this. We analyzed a little bit that problem. We saw, for instance, in the microstructure, it did not change too much the porosity or the pore size distribution, and we also saw that for some amount of superplasticity, the difference with the samples carbonate with bacterial nanocellulose was not, improving mechanical strength, but with nanocellulose it was increasing the mechanical strength.
Okay. The this is very interesting. I think you have to put that in an annex in your thesis or something like that, because it's important to show. I have two questions for your perspective in the future. I know that what are the fabrication in the field is complicated. Do you think that it's possible to put this nanocellulose in field operation to, for example, for improve the oil and gas casing cement or for the injection of the CO2?
I didn't hear you at first. Can you repeat the question, please?
Oh, I know that you study a lot of things in the labs and you run some numerical simulation, but in the future maybe this kind of cement will be used in the field, in an operation in the field, for the oil and gas industry or for the injection of CO2. My question is, if it's possible, or what do you think about the possibility to use this in a real operation, where the fabrication of this kind of cement is easy, it's possible to transfer this technology from the labs to the field?
I think the main problem in this case is going to be viscosity. I mean, we need to standardize the cement paste in order to have some similar thickening time and consistency to the one of that we are using right now, because actually we first need to have a good distribution of bacterial nanocellulose on cement in order to make the additive be homogeneous, and that the amount of bacterial nanocellulose that we use and superplasticizer and any other additive that we use should be similar to the ones that we are using now. I mean, having a large viscosity may have problems of workability. But yeah, if we can determine that bacterial nanocellulose, if we cure it at different temperatures, improves the cement property, and we can find a content of superplasticizer adequate for it, I think that we can use the cement on several wellbores. Yeah.
Okay, thank you. Congratulations for you and for your advice. Thank you.
Thank you, Martin.
Sorry, I was trying to unmute myself. We are done with the three reporters. We are now going to continue with the examiners. Let's start with Dr. Pique. Teresa, the floor is yours.
Thank you very much. Well, again, congratulations, Juan. It was a great work indeed. The whole manuscript, there's a lot of experimental results you got, huge amount of work, and the literature. I mean, you did a great job, like looking for literature to try to explain every result, why to relate it with what you compared to, or with what you found in literature. So yeah, I wanted to congratulate you on that. I had some questions. Well, most of them it's been already answered, but yeah, I also have this thing about the superplasticizer. I mean, it was even the double of what you use in the nanocellulose. I saw. I couldn't understand the second one you showed, Martin. The first one it's okay. It doesn't change the porosity. It's not actually it's the capillarity, the capillar porosity. That one I don't see the y-axis. I'm sorry.
Now, can you hear me now? Hello? Okay. Okay, in this case, where we have the blue dashed line, these are samples cured at 28 days and tested, and these are samples cured at 7 days and tested. And this relationship is the, let's say, the strength value at 28 days referred to the value at 7 days.
So it doesn't case. Okay. So yeah, well, that makes me remember. I did write some comments on the manuscript. I will give you when if you want to update your manuscript. This was one of them. I really don't understand why you use 7 days to uniform. It's at this point it's very hard to understand. I would have done it at 28, which is usually when the cells start hydrating or start the diffusion process. 7 days. Why did you do that? Why did you choose 7 days?
Well, initially, we had time to perform several tests, compressive strength test, and it was an easy job to do. So that's why we chose to do at 7 and 28, and also to see how was the strength developed over time after 7 and 28 days, and if there was maybe some difference during these stages.
No, I got that. That was really interesting. No, I don't understand why you uniformize at the age 7. Why is it why you make relative to 7 days of curing? It's not that the first time I see it, and it's hard to understand the evolution of cement. But at least for me, maybe there's something I'm missing. This is why I'm asking.
No, I mean, in this case, as we had the value at 7 days, we wanted to. We could have referenced at 28 days, as you say, but it would have stayed. It would be the opposite, right? The one would have been here, and here would have been, I don't know, 7.7, 0.7, yeah. But we chose 7 because it was initially 1, and we could see, for example, that after 28 days, there was a 45% of increase respecting the strength at 7 days.
Yeah, but the 7 days, there are different mechanisms happening, so maybe it's not the best one to use to compare. I mean, the cement curing is very unstable and changing a lot from 0 to 28. Then, unless you have supernormal activity or whatever, it usually stabilizes at 28. So you should use that stable ages to compare, because maybe at 7 there are different things going on. Like, for example, which is what takes me to my first question, superplasticizers usually behave, well, maybe if you use too much it can stop, and it provides more wettability to the cement, to the anhydrous cement. So probably you have a higher hydration degree when using superplasticizer. And one of your conclusions is about the preparation. Maybe you should have used a reference sample with including 0.35 of superplasticizer, which is the one you then ended up using, to have a really for real reference, because it's quite a huge amount when, like Martin said, when compared to 0.05 of bacterial nanocellulose. But that was just a comment. The other one about when you measure many the elastic parameters, you measure them in many different ways, which is it's amazing. I mean, you did it by dynamic mechanical analysis, ultrasonic waves, UCS, and TRX, the triaxial test. Have you, and for the model, yet you use homogenization. So I have there two questions. The first one is, did you compare all the results? Did you find anything interesting when, I mean, you have the elastic, it's huge work to have them in so many tests, so many different techniques. Were you able to see similarity between them? And the other question is, did they match with the homogenization model you used in your modelization? And the last one, which one would you choose? I mean, if you have to report elastic parameters, which one would you choose? Would you report the one you got with the homogenization, with the triaxial test, with the unconfined compressive strength, with the weights, or the DMA, which were the 5 ones you used?
So the good thing of having this amount, it's a good thing to have a lot of experimental results, but the bad thing is that compare them is to compare them is a hard task. I think I need to have a better comparison between all my results, and if I were to choose the ones one of the elastic model, I would choose the one of the experiment, which is the real one. But in the simulations, we saw that they were quite matching the results. The simulation was matching the experimental result as well, and it is interesting because the elastic model in this case was not fitted. It was calculated by the model, and we only fitted the strength, and it was calculated only by the model, and it's fairly it's similar to the experimental one.
The experimental is the unconfined compressive strength?
Yes. Yes, it's an actual compressive strength test.
Then there's something similar like what Selina said about the cracks and the porosity. What caught my attention is, can you go to the slide with the gel porosity, when you compare the gel porosity to the capillary porosity?
Yes.
I'm not very sure actually of how much the capillary porosity can go up, but it called my attention that it was higher than the capillary. Well, no, I'm not quite sure how much the gel porosity can be, but I think it should be lower than the capillary porosity. So what I thought is that maybe in this equation you use when you calculate the total porosity, you're missing the macro porosity. I don't think you can measure the macro porosity. Maybe you do. You can't measure the macro porosity with the MIP. When you mix, especially when you use superplasticizer, there are a lot of bubbles included. So those big bubbles that you might have measured by weighting the samples in the open, you miss them in this equation, and this might be reducing what I think that the gel porosity, the amount of gel porosity, which I think is a little bit high, because the gel porosity is the free space between those sponges that are the calcium hydroxide silicate. So, what do you think about that? Or did you include in your? And I couldn't understand that part. Did you include the macro porosity somewhere in this calculation?
In this case, the total porosity was performed by oven drying. So we just took a sample from the cement and we took the weights before and after heating. That was total cement, and we we don't know if inside the sample there is a bubble. I don't know. But we found that the values were really consistent, around 40% in this case. The reduction, I mean, capillary, the macropores, I think the MIP can, I think it can take up to 1,000 micrometers. But which we can say, I mean, that is capillary porosity until 10 nanometers. But yeah, I mean, we suppose that the macroporosity in this case was the total porosity. I mean, that macroporosity was included in the total porosity.
Okay. But you didn't subtract it. Okay. Well, I think that's all I want to ask. Again, congratulations on the presentation and on the huge work you do, which is quite impressive.
Thank you, Teresa.
Let me then continue. I think I'm the last of this sequence, Juan Cruz, so let me start. Let me ask a few questions related to experimental procedures. And one of the reasons is that there's always a challenge when we run experiments, and that is to distinguish what we measure, what we want to measure, and what we actually measure. And then I think that some of it happens in every experimental study, right? So let me start with the capillary porosity. It appears to be playing an important role in your thesis, and I'm not in this field of cement, but why make such an important distinction between capillary and gel porosity?
Let me go there. So we actually wanted to know what was happening in all pore range, let's say, by performing only MIP test result. We were obtaining results, but having the total porosity also helped us to determine the gel porosity. And I think it gives to the work a little bit more of more results to work on in this case.
Okay, but the question I'm asking is, why make a distinction between capillary and gel porosity? What is so magical about 10 nanometers?
Actually, that we took that from literature. I think for cement, it is considered that pores less than 10 nanometers are gel porosity, are gel pores.
And does it make sense to you? Do you actually believe in that? Does it make sense that we want to make a difference?
Well, it's empirical reason, so we just work with that. And for me,
I'm pushing you to tell me, is there a dramatic change in the physics?
I think it depends. For instance, in this case, gel porosity is considered to be the CSH porosity. So initially, to simplify the facts, we use this, but in order to have the real gel porosity of CSH, we should, for each sample, we really know to calculate the CSH porosity separately. And then we can say, okay, this is total, this is gel, and this is capillary porosity.
Well, let me suggest that's something that you may want to address in the thesis. Candidate answer means that you have 50 water molecules across. And there may be some meaningfulness in these values. When you mix the biopolymers in the Erlenmeyer flasks, how did could you see that they were settling in time? Was that creating a stable suspension?
No, the free fluid in this case, initially when we put it, is an homogeneous mixture, and this free fluid starts to appear afterwards.
Sorry, just the biopolymer in water after you sonicate it, does it form a stable suspension?
Here, you say.
Yes, correct.
Initially, no. For we have seen it was an homogeneous mixture, but I don't know, for probably on the micro scale it could have been different. Probably there is some sustain. Probably because the bacterial nanocellulose goes up, but I was not able to see that.
So if you left it overnight, it wouldn't settle. You wouldn't see clear water at the top.
I don't know. Water at the top.
Yes.
No, I didn't see it. I didn't see that.
Okay. And did you try that to the superplasticizer, to the biopolymer slurry, just to the biopolymer slurry?
No, I did not try that.
Okay. You see, this suspension test, just in a test tube, is an amazing, it's a simple but an amazing test to understand the electrical interaction between the different components. And so you may want to do it. I mean, it's insightful. Let me ask you about the LVDT, because, by the way, you did show a picture in your presentation that I didn't see in the thesis. Either a picture or a sketch of the installation of the LVDTs would be very, very important, particularly if you're trying to get bioparameters, right? Tell me, did you compare the strains that are measured with the inferred LVDTs, and you're measuring deformations, but when you compare the strains, did you compare against strain gauges glued onto the specimens by any chance?
Yeah, we initially started by using string gauges, but they were not working as we wanted. And as I said before, it's quite a hard working to perform this test. And we said, okay, if we had to add another complications with the string gauges, we prefer to have the same method for all, and we chose to use only LVDTs.
Okay. When you get to the point of determining bioparameters, you may find quite a difficulty using the LVDTs, at least in our experience. I'm going to get to just a second. Yeah, and so let me jump to the chapter 5, and then I will come back to what I think is the core of your work, which is the cellulose. In chapter 5, in the end, if you were trying to study the carbonation front, the diffusive reactive equation in finite differences in Excel. And by the way, you would have had 1% of the parameters or even less.
Sorry, it cut. Can you repeat the question, please?
Yes. I find that the numerical simulation is very sophisticated, but equally very complex, in the sense that, number one, and this is a statement, please, I look for your reaction. Number one, that you have a large number of parameters that you really do not fully grasp or have information for. Number two, if you do a dimensionless ratios type of analysis, you will see that there are just a couple of processes that are governing the behavior. So in the end, I wonder whether a much simpler simulation of a diffusive reactive transport equation would have been enough and more robust. Could you react to that?
Yeah, probably it would have been much easier, but we wanted to use this tool because it's actually a relative new model, so we wanted to apply it to our experimental test and to calibrate. I mean, to find the parameters of the model in order to improve it. But that was the main reason, and also it was developed by my thesis supervisor. Well, actually, he a student, a PhD student. He was supervisor of a PhD student who developed this program.
From the perspective of your work and for the usefulness of the results, and the alternative is also very valuable. So my last question really is about your mental model of what is cellulose, nanocellulose is. And I have an idea of, based on your comments about the thesis of your mental thought about it, but could you summarize it for us? If you had to tell us in few words what BNCs are and their key properties, how would you summarize it?
Well, initially, well, in this case, bacterial nanocellulose is. I wanted to go to the slide. Okay, so in this case, the bacterial nanocellulose that we use is it was developed by this bacteria, and it is a polymer with great crystallinity, with very high tensile properties, and in cement the problem is not compression, it's tension. So we wanted to see if this strong tensile material could increase the cement properties in this case, because basically the production is increasing, and for CO2 storage there is a thermally stable material that may allow to improve the properties of cement.
Let me tell you my summary of your thesis, and please really correct me where I deviate from your perception. I feel that you think that these are inert fibers that can cement, keep particles together like threads. And in fact, you have a sketch on that in figure 2.2, and that hold water as a sponge. Would that be a fair summary?
Well, in this case, we talk about the physical changes produced by bacterial nanocellulose, but we didn't explore the chemical changes that it may produces on cement. So I think we need to first see how is the chemical activity of how it modifies the chemistry and in cement in this case. But because we were seeing the large component, I mean, how it changes Polandite, how it increases hydration and everything. But we think that actually it's in one part because it's a strong material, but and it has a large superficial area, but it also we need to consider the chemical roles in this in play that we did not study on this thesis.
Okay, Juan Cruz, you say a few times that 5 or 6 times throughout the thesis that given the high specific surface, it absorbs much water, and that has an important effect in further hectalization, hydration, etc. And clearly changes the viscosity, and that there are equations that we can use to compute the changing viscosity due to the addition of high specific surface material. But that you clearly show that in your thesis as well. Now, I did some brief computations of how much water can be absorbed onto these nanofibers. And assuming that you have 100 meters squared per gram, and I give it a full nanometer of water, that means 4 monolayers of water, etc., which is probably not realistic. Probably the amount of water would be 10 to the minus 4 with respect to the amount of cement. Your water cement ratio is 0.44, so this would be minuscule. And so I go back and really invite you that as now you look at your whole thesis, like we, the committee, were able to do, go back and look at the whole thesis. And I think that some of those statements, put few numbers, and I'll send you my notes, and they may be wrong, so please, I apologize in advance. But put few numbers and double test your hypothesis and your mental model. For example, this likelihood that cellulose, while it is very stable in water in general, it has relatively high solubility at pH 10, and you are at very high pH with hydrating cement. And in fact, none of your SEM images, there is one that shows some fibers when cement is involved, but they look different. It's not the original fibers. So, just a thought. And all these issues of osmotic effects and yes, double layers and the surface charges could probably help you bringing an alternative hypothesis that could bring clarity to your results, which I find fascinating, even though I am outside this field. So I'll close with that my part of my comments. I'm not quite sure it was clear, but I invite you to look at what is BNC, and it's an alternative look at its potential role in cement paste. But you have great committee members here, so I have to be very careful now in what I say. The last word goes to your members of the leadership team, your advisors. So let me start with Siavash.
Okay, thank you, Carlos. Can you hear me?
Yes, we can hear you.
Yeah, thank you. Thank you, Carlos. Okay, Juan Cruz, thank you very much. First of all, let me congratulate you for this very nice presentation. It was very clear. As you answered already to many very good questions, particularly this last person who asked quite challenging questions. I will not going to ask more questions. Just I want to congratulate you for the nice work and to say it was a pleasure working with you. You are a very hardworking and serious student, and it was really nice to work with you. I would also to thank Diego opportunity to work on this project and on this collaboration. And I hope that we have more opportunities to work together in the future. And that's it. I give the floor back to Carlos.
Thank you, Sebas.
Thank you, Sebas.
Your turn.
Thank you, Carlos. I won't have any questions, but I will start with some comments. And first of all, I would like to thank you all the members of the jury for your presence and for having accepted to evaluate this work. It's a pleasure to have you online. I won't say here, but I really appreciate. I think that the quality of the discussion and the questions that you put show the interest of the topic and also of the results that were obtained by Juan, and this is the purpose of such defenses. So thank you again. Now I will give a few words related to the genesis of the collaboration. It's actually dates back more than 10 years ago when Diego was here as a postdoc in Paris. And then we continued to collaborate and to work together. And I think it was more or less 4 years ago. Diego called me saying that he had a very good student that he was trying to convince and to involve him in a PhD track in Patagonia. And they had this topic about the effects of BNC added into cements. And so we stepped in and we started to work, and this is where Juan Cruz appeared in the picture. Then, so the idea was to collaborate and for Juan Cruz to come to Paris, and I have to mention that he obtained a very prestigious fellowship. It's called a fellowship for doctoral studies, and so he managed to win this fellowship, and this is a good point that we could mention here. Well, as you have seen, Juan Cruz demonstrating that he's able to perform a lot of tests and to the results that he obtained. Well, as pointed out by all of you, there are things that I think Juan Cruz needs to sit down now that all the results are available, and maybe to continue the work of analysis and the intercomparison between all the tests. Well, I think the zero question that not the number one, but the very fundamental is the one that Carlos put. What is BNC and what it does? Well, it brings me to one of the comments or questions of Antonin also. This material and its effect on cement have not been fully studied, and I think we still have some space, and some questions are still open. So, but I think that with the results that was obtained, we advance a small step, and we still need to work on the interpretation of all this data. But anyway, this was a challenging work, and a good step was achieved. In terms of modeling, Cruz learned a lot. He had to enter into the implementation that was produced by Valin a few years ago. He did that and improved the model to include some new phenomena that were not accounted for before. Regarding the question of Carlos and the fact to use simpler approach. Probably I agree. I agree, but it's always good to start with simple modeling approaches, of course. I think Juan Cruz answered well, saying that the tool was available and developed by the PI, so sometimes you have no choice. But well, I always let the choice to the students, of course. But I think it was not so difficult for him to start from something that was ready and operational. Working. We need to check to be clear on the answer for you, Carlos, because the problem is really highly coupled, and separating the diffusion and the chemical reactions from the mechanical aspects is probably doable in some cases, maybe not in some others. So in some situations, there is some feedback of the pore pressure. For instance, when you carbonate the cement components, produce water, and this water can induce high pore pressures, and it would change the chemical reactions. Well, not the chemical reactions, but the progression of the chemical reactions. So it was checking carefully. But if indeed we can decouple, then you are totally right, of course. And well, so in the end, I think it's a really good piece of work that you did, Juan Cruz, and well, I was really happy to work with you these 3 years and to have this nice collaboration. And as you see, we have it's not finished. We have a lot to work on still, and to continue to value your work and publish it in the literature. So thank you again, and thank you, Carlos.
Thank you.
Thank you, Jean-Michel.
Diego, I think that you have the last word.
Okay, thank you, Carlos. And thank you all the members of the jury for reviewing the thesis and for the excellent question. I think Juan Cruz tried to answer all as better. Just I would like to say a bit about the past, about the genesis, as Jean-Michel said. Juan Cruz began to work in his thesis with another student who are doing the thesis also at the same time with Juan Cruz, with Analia Vázquez, which is the co-director of this thesis in the Universidad Nacional de la Patagonia. And both students will study bacterial nanocellulose in cement. Well, finally, the other student cannot finish because some personal problems, so we have to continue with this with Juan Cruz in Comodoro Rivadavia in the 2017. So that was sometime we had 2 works to study the BNC, but finally one of these works didn't continue. So that could be one of the explanations that we don't have the real genesis of the bacterial nanocellulose as additive of cement. But I think there is a lot of work to do related with bacterial nanocellulose. We began this collaboration with the Institute of Polymer Technology and Nanotechnology with Analia Vázquez, and now there are many other researchers working in this institute and study this bacterial nanocellulose which is produced by this institute in Buenos Aires. The idea of doing the joint work, I think Jean-Michel explained very well. We began to study the numerical modeling of CO2 storage in the 2011, and we continue to work with that with Jean-Michel. And then I looked Juan Cruz in Comodoro, who was an excellent student of geotechnics and civil engineering there, and it was fantastic that he wanted to join us to study. The thing that when I told the idea of doing this type of research, I said, well, there is a possibility to do a research stay in France. And the first thing that he said is, well, that I didn't understand French. Well, this doesn't matter because he speaks Spanish also. But nowadays he speaks very, very well French. So this was another achievement of Juan Cruz, not only doing his PhD thesis, if not also learn French, and he is very, very well French speaker. Just in order to work a bit about the scientific work of Juan Cruz, I think he's grown a lot from the beginning. At the beginning, he was a bit stubborn with some things and about his thought about the findings. But finally, he involved in this type of research in both country and state in these two things, sharing with a lot of PhD students in France, did that he grow as a researcher. I think it's really important for him and for also for the university of his coming, which is the Universidad Nacional de la Patagonia. It's very important for him and for the institution, this thesis, this doctoral thesis. Personally, I know Juan Cruz as very well. I try to continue with him also in Paris, visiting him there, and I think he's a hard work student and now in engineering, of course, and I think he could perform or continue performing research, postdoc or an academic position if he wants to continue with this work. Yes, to continue with this line of research. This scientific evolution of Juan Cruz and also his personal evolution is part of this exchange between both universities. I think it's very important for him and also for an institution as Universidad Nacional de la Patagonia, which is a small university in the south of Argentina, but it's interesting to have this exchange, international exchange. Just I would like to say something in Spanish because there are many people ask just in order to say something in Spanish. Sorry for people who don't speak Spanish. Le quiero agradecer a toda la comité organizador de este evento en Comodoro Rivadavia, a su directora del doctorado, Adriana Pajares, bueno, y a toda la gente que estuvo involucrada para que esto salga adelante en Comodoro. Y bueno, tenemos en Comodoro hay el primer estudiante de doctorado de este comité doctoral de la Facultad de Ingeniería, así que creo que es un gran logro para la Facultad de Comodoro. Y nada, agradecerles por todo el esfuerzo que hicieron para que esto salga adelante. That's all, Carlos. You have the floor.
Thank you, Diego. And so Juan Cruz, in summary, 3 languages, an experimentalist, and a numerical model. We are showing congratulations, and the committee now needs to deliberate. So I guess, Diego, you will transfer us to another room. And to be ready for that, let's say that the committee will take a 5-minute break, and we'll reconvene in 5 minutes in the other room. Okay. Thank you to the committee and to all who were in the audience. Juan Cruz, stay tuned, we'll call you back. Thank you.
Thank you, Diego y Carlos. ¿Me escuchás?
Sí.
Ok.
Ahora van a hablar el presidente del tribunal.
Juan Cruz, well, we cannot see.
Trying to fix it.
Okay. You don't need to show me, just you are the important.
Just 1 second.
Yes, if you stop sharing the presentation, that should be one.
Okay. Ahí.
Okay, so
Mm,
probably Diego is controlling your camera.
No, I can. I will try.
Okay.
Juan Cruz, where is it?
Un minuto, Diego, ¿eh?
I can write here. Okay. We have to wait 1 minute.
Okay. Okay.
¿Sí? Uy, ¿dónde estoy? Sí. ¿Por qué me veo en chiquito?
¿Tú puedes activar la cámara que sea de tu computadora?
Sí, pero por acá no. Ah, por ahí. Por acá. Ahí está. Yo no veo bien la...
¿Y no ves? Ah, no ves la imagen.
Lo veo pequeñito, Carlos.
No.
Perdón.
Claro, se veía mejor ahí.
Me ven en... can you see me small, right?
Yes.
That's not good.
Yes.
Tiene sonrisas.
In any case, probably we can proceed.
Okay, yes.
Well, we are zooming here. excellent Juan Cruz. On behalf of the committee, I have to say that we were all very positive about your presentation, the depth of knowledge, your intellectual curiosity, and your research commitment and dedication. And I have to say something that was not mentioned, that all this happened in COVID time, which made it all the more difficult for everybody around the world, particularly young people advancing their PhD. So, sincere congratulations. But furthermore, from an academic point of view, you have shown great mastery of very complex disciplines. The materials, the mechanics, the modeling, the experimental work, the application of intricate cement technology to a very complex problem of CO2 geological storage under pressure and temperature, something that is critically needed for the future. So, based on all these reasons, the committee unanimously congratulates you for your accomplishments, and I believe that this will give you a PhD degree both from École de Pont and from the Universidad Nacional de Patagonia, San Juan Bosco. Congratulations.
Thank you so much, Carlos.
You have the last word.
Yeah, I was thinking this. I didn't resay this. I would like to thank you all members of the jury for being part of my thesis. I would like to thank the doctoral committee of the Universidad Nacional de la Patagonia San Juan Bosco, and actually I have a lot of people to say thank, but I would like to thank my family, my friends, the laboratory of the university, Alejandra, Oscar, that they were always supportive, to the faculty of engineering, to the rector's office. And also, I would like to thank all the administrative staff of the École de Pont, and I'm really thankful for all of you, all the help that I received, and I think I done some of my part to complement this doctoral thesis. So. I would like to thank you all, to be all the ones that we present here and online streaming. Thank you so much.
And on that note, I think that we close this act to the end, we bring it to the end. So, Jean-Michel and Diego, thank you all for the opportunity of being here. Bye-bye.
Thank you.
Bye, everybody.
Bye-bye.
Bye-bye.
Goodbye.
No lo cortes.
Congratulations.
Thank you. Ok, ¿me escuchan ahora? Nada, gracias por todo. El tema es que cuando pongo este micrófono hay un eco, entonces... ¿Ahora? ¿Se escucha? Ahí está. Bueno, nada, les quiero agradecer. La verdad, creo que son los mejores profes, directores que pude haber tenido. Me ayudaron muchísimo en todo esto. Me hubiera gustado que hubieran estado acá, bueno, pero es muy lejos la Patagonia para... pero bueno, sí estuvieron presentes en línea y eso es muy importante. Y nada, les quiero agradecer con todo el corazón por estos 3-4 años que tuvimos. Y nada, vamos a ver cómo sigue y nada, les agradezco de todo corazón.
Gracias a ti también, ¿no?
Gracias a ti por el trabajo y todo. El trabajo que hiciste. ¿Sí?
Ha ido bien, ¿no? La presentación, muy bien.
No, al principio no, porque me distraje, qué sé yo, creo que la de ayer estuvo un poco mejor, ¿no?
Estás estresado, pero
Fue bien, pero...
Bueno, me alegro.
bueno.
¿Sí?
Bueno, dale, nos vemos acá en 2 días, ¿no? No sé cuándo venís. Ahí nos juntamos y hacemos algo acá.
Después de bueno, me voy al aeropuerto si no llego.
Buen